Welcome back. We are looking at the AP Physics C Electricity Magnetism, the E&M exam. We are looking at the year 2011, a fine vintage of a year. This is question 3, and this deals with Ampere's Law. So it looks at magnetic fields due to current carrying wires. And what we have here in this problem is we have a long, so let's just call it an infinite length wire, with an inner radius A and an outer radius B. So this wire is hollow through the center. And it's carrying a current I naught that has a uniform current density. And this is so nice for us. The current density is uniform, as shown in the figure above. Now, we haven't played with a current density yet. We've just always said that the current exists. But there's a current density traveling through this wire. We're going to see it works very similar to how we work out Gauss's law, but we'll see that whenever we get into amperes. Okay. Using Ampere's law, derive an expression for the magnitude of the magnetic field in the following regions as a function of the distance r from the central axis. Well, what we have to first think about is, what is Ampere's law? And Ampere's law in general states that if we make a closed path integral of a length around some region. So let's kind of look at this cross section here. If we made a closed loop, so there's a closed loop, a nice circle, around some region, then we could write that as the closed loop. And what we're trying to enclose here is we're trying to find some amount of B field through some amount of length. Okay, this is a dot product here. These are acting in the same direction. And if we go through this length, this will equal mu naught times the amount of current enclosed within that loop. Okay, so this is very similar to Gauss's law for electric fields, where a closed integral of an electric field by an area equals the charge enclosed over epsilon naught. In this case, we're just looking at magnetic fields, and we have this mu naught, the magnetic permeability of free space, existing in the numerator instead. So it's a very similar problem. When we do this, though, we have to recognize that this here is a length, and since we're going to typically do these for circles, we're going to be talking about this length being the circumference of a circle. And typically, circumference of the circles are just 2 pi r if we're going through the whole path. So that's what we're looking at here. In short, because like I just said, these are circles, this equation normally for us is just going to boil down to the B field times 2 pi r, the circumference of a circle, equals mu naught times whatever current we have enclosed within that. And if we kind of take a look at this right here, we're between A and B, that would be like, what's the current in that region there? Okay, so that's just what we're going to be playing over and over again. Very similar to Gauss's law, but just with B fields. So if we use this idea and we say, okay, let's draw some Amperian loops here. What is our magnetic field inside of this region, at this region R here within A? Well, first, since we're using Ampere's law, let's just write out Ampere's law. At some point, you're going to get a point on an AP Physics C test like this just for writing out the correct equation. So Ampere's law, like I already showed, that's just the closed integral of a B field dotted through some path, and that equals mu naught times I enclosed. Okay, so boom, we just got ourselves a point. Even if I don't know what's going on, I know that's Ampere's law, I got a point. Yay. If you don't know what to do from here, move on, but you got a free point. Now, if we go back to this here, if we look at Ampere's law, and I say, okay, I'm at some radius within A, I'll just draw it there. Have I enclosed any current at all? Well, the current's running out here. So I've enclosed nothing. So because of this, my enclosed current is 0. Which means that when I apply Ampere's law here, that a B field through some circumference, 2 pi r, that has to equal 0. Which means that the B field equals 0. And that's it. What an easy part. I'll say Tesla because let's get proper units. But that's it. We're inside that current. There's no current running through our Amperian loop. There's no B field. Woo! What a great one. That was 2 points right there, just for writing an equation and saying it's 0. Okay. Now, if we go to A is less than R and less than B, then we're saying as we move out from here to here in the radius, then how does our B field change? Because at this point, when we draw our Amperian loops at some radius R, we are getting some amount of current going through. And that amount of current depends on how big that loop is going to be. So what we need to do here is we need to look at a current density. We're still using the same equation. We're still using this idea that a closed integral of the B field through that circumferential length equals mu naught times I enclosed. And it's still going to give us B times 2 pi r equals mu naught I enclosed. But the tricky part here, and we saw this with Gauss's law if you've been watching these videos, what is the current enclosed here? Well, we know that there's a current density. What we're going to use for a current density, we're going to say that a current density is the variable J. Okay, that is the variable for current density. So what we're going to do here is let's try to figure out how much current exists as we move throughout this wire. Well, that current density can be thought of as what is the entire current that we have, I naught, because I'm using a capital here just because I believe they use a capital in this problem. So that's the amount of current running through this wire, and then, well, that current density as a function of cross-sectional area, well, what is the areas I have here? Well, I'm just looking for what is the current density within this region. And to get that, I can take the entire area out at radius B minus that area tucked into radius A. That's the whole minus the whole. Okay? So what we're going to do here is we're going to say, well, that radius all the way out at radius B, the large one, is pi b squared. That gives us the larger area. Okay, so this is the, right here, this is the large area. And then I'm going to subtract from that pi a squared, because this right here is the whole we're cutting out. Okay? That is our current density. And we just did that as a function of cross-sectional area. Okay? So what we can do here is we could say that our enclosed current then, because that's actually what we need here, our enclosed current is equal to the current density multiplied by whatever area we have that we're enclosing. Okay? Well, the area that we're enclosing, if we go back up to our cross-sectional area picture, the area that we're enclosing here is out to some distance r, because that's our Amperian loop, minus out to that distance a. Okay? So we're enclosing all of this in the middle. So whenever we can write this down here, well, we already know the value of j here. This value of j is just I naught over pi b squared minus pi a squared. And then the area we have enclosed that we're multiplying by is just going to be pi r squared minus pi a squared. Okay? If we take a look at this real quick, we can quickly see that if we pulled pi's out of the numerator and the denominator, all the pi's are going to wipe away. And we actually see that our current enclosed here is just going to be I naught times r squared minus a squared over b squared minus a squared. Okay, that is our current we're actually enclosing here. We just got that by using the density. So now that I have this current enclosed, and that was the hard part here, we've always done similar things like this whenever we do Gauss's law and we're looking at the charges enclosed. This time it's just current. we can dump that right back to where it belongs. So when we do this, we use the color red here, we're going to get B times 2 pi r equals mu naught, and then our current equation, which was I naught times r squared minus a squared over b squared minus a squared. And then we just need to divide each side by 2 pi r. We divide each side by 2 pi r. These divide out, making life nice and easy for us. And we see that the B field at some radial distance away from the center of that wire is given by this. So that's very nice and easy for us. Okay. Now, going in the middle of the wire, those are always the hardest problems. Whenever you're tucked inside the object, those are the hardest ones because you need to figure out how much current you're actually enclosing there. Whenever we get to this point, where we get to the edge of the wire, we're all the way out at the very edge of the system here. We're sitting out here now. These, once again, become a little bit easier because whenever we write Botzer law, when we say that the closed integral of the B, the magnetic field, dotted with some circumference equals mu naught I enclosed, well, in this case, we know how much current we are enclosing here. We know in this case that this is just going to be B times, well, that radial distance we're going out. In this case, that 2 pi r, since we set r equal to 2b, and excuse me, if I go back up here, we're not sitting at b, we're actually sitting at twice b, so we're sitting kind of out here somewhere. This is 2b. Okay, so we're sitting out beyond the wire. Since this is normally 2 pi r, but we've called that r value equal to 2b, we can substitute that in there. So what we can say here is that this is going to be 2 pi times 2b equals mu naught times I enclosed. Luckily for us, because we're sitting all the way out here, we are already enclosing all of the current inside our Amperian loop. All the current is tucked in there. So we just have to rewrite this as saying, well, this I enclosed is just I naught, and we can say that B times 4 pi little b equals mu naught I naught, the total current. And that means just solving this for B, we see that the B field is equal to mu naught I naught over 4 pi b. So that was actually an easier one there as well. Still just using Ampere's law. This time we just had to recognize that we could put in 2b for r, and that the current enclosed was the entire thing because we were outside the system. So that was nice. So that right there, if you just worked through those 3 Ampere's law, that got you 1, 2, 3, 4, 5, 6 points. And really, we only had to do like math once. So you just pulled 6 out of 15 points for doing kind of one math problem and just understanding how Ampere's law works. So that's a pretty nice problem there. Now, on the cross-sectional view of the diagram above, we need to indicate the direction of the field at point P, which is at that radial distance of 2b away from the axis of the cylinder. So if we go back up here, and what direction is this B field going? Well, they've told us here that the current is going into the page. So the way we can figure out what direction the magnetic field is going is we take our thumb, our right thumb, because this is going to be a right-hand rule, and we stick our thumb in the direction of the current, which is into the page. What we now can see is that when we curl our fingers are going in the direction of the B field, in the direction of the magnetic field. So I know that my B field is traveling around in a circular path like this, which means that when I get to point P, my B field is going to be tangential to that going down because it's going to be continuing that circle. So what we see for point P right there is just the arrow we have right here going down and to the right. So that's the direction of the B field there. And we got that just for the right-hand rule. Okay? And that line, as we see, should be, hopefully, perpendicular to that circle. Okay? Because this is making a nice circle here, so we're good. So that's an easy one. That's just a right-hand rule. There's 2 points there just for that. So if we got 6 from doing one math problem and 2 from a right-hand rule, got 8 out of 15 for doing nothing yet. For part B here, at point P, an electron is placed there. Describe any electromagnetic forces acting on the electron and justify your answer. This is a little bit of a trick question if you're not ready for it. A lot of people like to say, oh, like we put the electron there, it's going to be pushed by the B field because of the F equals QV cross B equation. But this electron is at rest. If we look at a point charge acting in a magnetic field and what the force is acting on it, we know that F equals QV cross B. That was one of our right-hand rules. V equals 0 here. Anything multiplied by 0 is 0. So there is no force acting here. There's no force due to the magnetic field, and since there's no electric field either, there's not any electric field force being acted upon this. There's not any electromagnetism acting here. So it's just nothing. And we can just justify that answer with this right here. F equals QV cross B, V equals 0, F equals 0. And we're done. That right there is another 2 points. So we just went 10 out of 15 for doing really just one mathy part in the middle here. So I'm loving this problem. The next part, what they've done is they've taken that wire and they've made it solid. So there's no longer a hollow opening in the center of it. It's just a solid wire of radius B with a current I naught. They said the magnitude of the B field here is given as a function of R, and this is the B field here. So I'm just going to write that again. We know the B field as a function of R is given as mu naught I naught R over 2 pi B squared. Okay, so I just wanted to make sure we have that, because that's probably going to be important. An experiment is conducted using a particular solid cylinder of radius 0.01 meters, carrying a current of 25 amps. The magnetic field inside the cylinder is measured as a function of R, and the data is tabulated below. On the graph below, plot the data points. Oh, this is great. Anytime we get a plot, I'm loving this. Plots are just free points for us because we learned back in middle school how to plot things. And what we want here is we want to plot the magnetic field B as a function of the distance R. So since B is dependent on R, B is going to be our y-axis, R is going to be our x-axis. If we look at our units here, just because that's important, I see up here radius is in meters, so let's put this in meters. The B field is in Tesla, and all of these values are times 10 to the minus 4. So let's just say that this is the B field as measured in times 10 to the minus 4 Tesla. Okay? And let's just plot these up. Looking at my spacing here, I've got a few thicker lines. And for my x-axis, I've got 2, 4, 6, 8, 10. So that's a total of 5. 1, 2, 3, 4, 5. So I can go 0. And then 0.002, 0.004, 0.006, 0.008, 0.01. That's nice. On my, we'll just tick these so that we know where they're at. On my y-axis, I've got 1.2, 2.7, up to 6.4. I've got 1, 2, 3, 4, 5, 6, 7 lines going vertically. So if my max is 6.4, let's just count off by 1. 1, 2, 3, 4, 5, 6, 7. And then we just got to plot this. You can just skip ahead at this point. You know how to plot this. So here we go. Point 2 is at 1.2. So whoop. Well, come on, work with me. Bing! Let's see, 0.4 or 0.004 is at 2.7, so 2, 2, 4, 6, 7, right about there. This does not like to plot. 2.7 should be about there. For 0.6, we're at 3.6, so that's 3, 2, 4, 6. For 0.8, we're at 4.7, so there's 4, 2, 4, 6, 7's about there. And for 0.01, we're at 6.4, so 6, 2, 4. Now, we've labeled our axis, we've properly plotted our points. The one thing that you must do is draw a straight line that best represents the graph. And they ask for a straight line, so you better pull out a straight edge or fold your paper over to draw a straight line here. I am going to do this with a line tool. And this is just a best fit. You're just trying to do your best here, so let's just fit this data as best as I can. Boink. Okay, good enough. Cool. So that's my best fit. There we go. That right there just got you 3 points because you can graph like you did in middle school. And if you're keeping score at this point, you just got 15, or you just got 12 out of 15 points. No, 13 out of 15 points for doing one math problem in the middle here. This question has 5 written all over it. Okay. The only thing we need to do at this point is we need to use our slope of the line to estimate the value of the permeability mu naught. Okay. Now, when you're using the slope of your line, a issue a lot of people fall into is they like to use these points that are given to us. They like to use this up here. Don't do that. Those points are not the points that your line represents. If I were to use, for instance, the points at 0.04 and 0.06, my line would actually be this right here. And that's not what my line of best fit is. It's clearly different. What we want to do is we want to look at our line of best fit and find 2 good points that we can accurately read from that line and use those instead. So if I kind of look in here at this line, I've actually got a pretty good point right here. Notice how it perfectly crosses that crosshair. And that's actually going to be at 0.009. And I also have a pretty good point. I want to try to pick a point pretty far away to get a nice smooth set. I actually have a pretty good point right about here, down at 0.001, because that point is sitting at 24, that is sitting at 0.6. And this up here is sitting at 5.8. Okay, so those are the points that I have from my graph. You'll have different points. Okay, all that matters at this point is giving those values. You're going to calculate your slope the same way you always have. y2 minus y1 over x2 minus x1. Plugging in the values of your y2, which for me was 5.8 minus, and then down below it was 0.6. I'm just reading those from my y-axis. Divided by, and then my x2 was out at 0.009 minus, and then my x1 was all the way back here, 0.001. Okay? This gives me a value of 5.2 over 0.008. And I guess we should calculate this real quick. 5.2 divided by 0.008 equals 650. Now, something you want to be careful about here is while that gave me 650, that is 650, but my B values up here, these were all times 10 to the minus 4. So even though this gives me 650, this is actually 650 times 10 to the minus 4 Tesla per meter, which I'm just going to write it as 0.065 Tesla per meter. Okay? So that's what my slope is. Your slope might be a little bit different, but that should be pretty close there. Now, that still hasn't given us what the value of mu naught is. That's just what the slope is. Well, we know that that slope, that change in y over change in x, that slope represents for us the change in the B field as a function of the radial distance. And we know values for our B field here. If we go back up to what they told us in this problem, we know how the B field changes right here. So what we can actually say here is that when we're looking at this, we can say that this slope is equal to mu naught I naught r over 2 pi b squared, I believe it was. Was it b squared? Yeah, b squared. Okay, and since that B field is just varying as a function of r, this r here is going to pop up there. And what we actually see is that the B field, or the radial distance, cancels itself out. So we know in this way that our slope, our value of 0.065, is equal to mu naught I naught over 2 pi b squared. Just like that. If they give us some values here of this, and I gotta kind of fix some things here. They gave us some values in this problem that we can use. We know what the radius of the cylinder is, and we know how much current is passing through it. So this radius here, this is value B. This current, this is value I naught. So when we go down here, and we're looking at this, well, we can solve this out. We can say by multiplying the 2 pi b squared, and then by dividing by I naught, we can say that mu naught is equal to 0.65 times 2 pi. That b value is equal to 0.1 or 0.01. So we can say 0.01 squared, because that's b squared, divided by the current, 25 amps. And when I do this, let's see what we get for a value. I get make sure you enter this correctly. I get, oh boy, this is a tiny one. I get a value of 0.0000016 Tesla meters per amp. And if we wrote that in scientific notation, I forgot a zero. This is 0.065. So there's an extra zero right there. Whoops, I knew I forgot something. So this is going to be equal to 1.6 times 10 to the minus 6 Tesla meters per amp. Meters. Okay? But we just got that using the slope. That last part, that was only worth 2 points. That right there was just as much math as we did all the way up here with the current density. So honestly, if I got to that point, that's an easy one to solve. But if I'm running out of time, I'm moving on and coming back to it in the last few minutes because I know I can get that pretty quickly, okay? So that's all we're looking at here for this problem. That's all 15 points floating out. Make sure you graph if you see a graph there. Those are probably the easiest points you're ever going to get on an AP test. Make sure you draw that line nice and straight. But the Biot-Savart law, or Ampere's law, excuse me, which is kind of moving from Biot-Savart, Ampere's law is very straightforward. You're just looking for a current enclosed, and you're just surrounding it in a circle. Okay? So once again, this was the AP Physics C E&M exam for 2011, question 3. And with that, we're finished here. Take it easy. Yeah, I bet you could buy like at least a tiny hippo if you had to.